So inform to your known peace, because there is some small miscommunication in this morning that it got displayed as class will be at 3 p.m. Okay, but there is some typo error there or something went wrong. But inform to in your network who are regularly joining the discussion forum of this that today morning session will be there. Is there? Okay. Okay, I hope. Shall we start, Vijay?
Yes, sir.
So, okay, let us start this today's day 5. Okay, so good morning to everyone. In this thing, I'm trying to cover the concept of nonlinear regression, particularly second order polynomial and cubic order polynomial. The quite interesting points what I am trying to cover is how to fit a curvilinear approach kind of a data, and how to know whether we need to stick on to the second order polynomial or third order polynomial, or is it fine with the straight line fitting when we have a partial curvilinear approach. Okay, so we will start the discussion with nonlinear regression, and later uh, we will go with the another concept called generating random numbers. That is a kind of a simulating random numbers with various probability distributions, and how to see some important characteristics and properties of distributions, relation between the distributions. Okay, fine. Let me share my screen with R. Fine. Today directly we'll do, because there are small codes. That's it. So we'll do directly. I'm using, okay, that entire line of thing is about the nonlinear regression. Okay, I'm using one particular data called the data is the data of dugong data. It's a one kind of a species animal, okay, a kind of a mammal, okay, dugong, where the data is related to the age and its length in meters. Okay, they want to estimate, given an age, how much length can be I mean given length, what might be the age of that particular animal. Okay, so this is the about the data. Now when we start understanding this data, we will come to see some kind of a pattern, that it is a slightly curvilinear, where the straight line approach, the straight line fitting is not that appropriate to that particular partially curved kind of a data. But the question arises, what sort of a non-linear approach we have to use to fit this particular data. Okay, so where we start with second order polynomial, and then we go with cubic polynomial. And again, one more question do rise, that once I fit the second order polynomial, is it covering the maximum number of data points across that particular pattern of that data points? Now, for which we have one method, that is ANOVA. Using ANOVA, we can see whether the straight line fit is sufficient or the second order polynomial is sufficient. At the same time, suppose uh, further, if we say that second order polynomial and first straight line have some significant difference, then we need to go a little further to make the model little complex, that is with the cubic order polynomial. Okay, where again you fit the data with respect to the cubic order polynomial, and then again apply the method of the technique of the tool of ANOVA to see whether we can stick to the second order polynomial or we need to go with the cubic order polynomial. Okay, that means it is nothing but at every step of model fitting, you need to have a check whether the straight line fit is enough, or we need to go with the second order, or the second order is enough, or we need to go with a cubic order polynomial. Okay. Now, what we will start with the, okay, we'll start with loading the data. Today we are using some different format of loading the data where it will enable the pop-up window. Okay, run. So I'm choosing the data where I have K.B.N webinar. In this I have okay, now data is loaded. You can see the data here, age, and this is the length in meters. Okay, right now we're attaching, we're directly calling the variables. Let us use the function called attach. Okay, and then let us see the summary. Now first, in the basic previous discussions of previous sessions, what I conveyed is first look at the data before you go to model. So the first look of the data shows in differently that you see the median 9.5, mean is 10.94. There is a slight difference, a marginal difference between the mean and median. Now, how to identify what the data is of almost normal or not is, look at this when compared to this 10.9 or median. If you say 9.5, third quartile is 15 and first quartile is 5. So when we see this, when we have the box plot of age, let us see that also. Box plot of, let us see age. Now, now see this, it is slightly having major area, higher, I mean, major portion of area on the upper side of the median. So data is slightly skewed. Data is slightly skewed, and you can see this first quartile and median is very having a very closer distance. But at the same time, I mean, in simple to say, the median is not exactly at the center. It has deviated towards, shifted towards the first quartile rather than the third quartile. Okay. Now let us see what about length. Length, you see, length is also deviated towards the third quartile, 2.4 and 2.5. So majority of this means that majority of the observations out of the data set what we have are concentrated to the left side of the median, and a little lesser to the right side of this particular median line. Okay, fine. Now let us understand the plot now. How the plot look like. Now, what observations we can make out of this plot? Given a length, we need to estimate the age of that particular animal. Okay. Now, so when I have the straight line fit for an assumption, I mean for a virtual, I mean intuition kind of a thing. If I have a straight line fit like this, okay, I'll be losing these points, and I will claim that these are all outliers. Okay. If I have a straight line fit like this, I'll be losing these coordinates. Are you able to see my screen now? Yeah. Okay, fine. Okay. Now if I draw a straight line like this, if I have a draw a straight line here, then I will, the majority of the data points should get connected. But these points, this small cluster of points will not get connected. Suppose if I have a plot like this, I will get a line like this. But still, I'll be not be able to cover some more points which are not in the same pattern of this trajectory. Now, what it gives us is there is some sort of a slight curvilinear approach in this data that start from this, and there is a required of to bend the fitting of the curve and then a little move up. So what we try to do is in our visual observation, what we can make or figure out is, I think straight line may not be a good fit, but we need to look for a curvilinear kind of a model fitting for this particular data. Now, what sort of a curvilinear approach? Is it second order is enough, or cubic polynomial we have to go, or any other thing we have to go? Okay. Now let us bluntly, because we'll start with fitting a linear regression. Yesterday we have done how to do that. It is nothing but LM. This is your dependent variable and this is independent variable. Let us see that. Let us run this, and we got the model. We got the model. The model is minus 44.567, 23.772. This itself is creates some sort of curiosity. Given a length, we can predict age, right? So intercept cannot be a negative value, okay? But having observed this, let us see the R square value. R square is 0.6883. Let me note somewhere here. The R square is 0.6883. Okay, or adjust the R square also you can take, but still model is significant. Model is significant. Okay, so today I will discuss one more point, that model will be significant, but however you have to depend upon the model adequacy and minimum mean square error, sum of squares due to error, that has to be, that is residual standard error should also be to be considered. Okay, now let us start fitting that line, AB line. See, when I had this AB line, the points are little farther, right? Majority of the points are not in and around the straight line. So I feel this may not be a good fit. This may not be a good fit. Then what we do is, I'll have a second order polynomial, that is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 square. Okay, beta naught plus beta 1 x1 plus beta 2 beta 1 x plus beta 2 x square. Okay, I repeat again, y equal to beta naught plus beta 1 x plus beta 2 x square. Okay, so this is the way to indicate that x square. Okay, now running this, look at the first I will have a look at the R square. Okay, 0.7729. The previous one was 0.6883. So when we have the second order polynomial, the information about estimating age of the particular data is improved from 68% to 77.29 R square percentage. I mean, explain the variability in age improved from 68.83 to 77.29. Okay. Now look at the mean square error, residual standard error. It is 4.48. What about here? It has come down 3.90. So when compared to with these numerical quantities, when compared to the straight line fit, the second order polynomial is comparatively better. But we need an evidence to claim that the second order polynomial fits for the data, rather fits better for the data than that of the straight line fit. We can do that. Before going to that kind of a validation or comparison between which method to be uh, fixed for further prediction, then use this another function called having a smooth line on this particular data point. Now see, this is obtained, this kind of a, I mean, this lines of smooth dot spline is built upon the predict of model 2, method 2. Method 2 is nothing but your second order polynomial. Okay. And this is the fit. So when compared to the straight line fit, you see this curvilinear fitting with the second order has covered majority of the data points. Has covered majority of the data points. We cannot do this because it is extreme observation. This is the best example of extreme observation. And this might be outlier. Okay, suppose if I have a trajectory like this, it might be outlier, or these two may be treated as an extreme observations. Okay, now one Graphically, one more support what we got is, first what we have observed numerically, the R square was better in second order polynomial. Residual standard error was little lesser when compared to the straight line fit, and graphically the curve what we have fitted over the data points is connecting majority of the data points rather than where the straight line fit is not to that extent. Okay, but still we need to generate a hypothetical framework to test whether the regression sum of squares between the second order polynomial is equal to the regression sum of squares between the first straight line is equivalent or not. There we use a technique called ANOVA. See, most of the time you might have understood and practiced that ANOVA is used to compare more than two independent populations. But in modeling aspect, we can use ANOVA or F statistic to compare the regression sum of squares of two models that are fitted on the same data. Most of these applications are can be seen in econometric modeling, like you can see this Chow test or some other techniques are available where you have to compare two regression lines, and the technique here it is ANOVA. Okay, now when we use this technique ANOVA, let us see, it will build a model 1, this is model 2, and this is the regression sum of squares with respect to model 1, and this is regression sum of squares with respect to model 2, and the p-value is 0.006, indicating that there is a significant difference in explaining the in having the minimum residual error with the second order polynomial and first order polynomial. So in the sense that the second order polynomial is quite better than the first order polynomial. Fine. Now we are at the benchmark that the data fits for second order. Is that final, or still can we connect this particular data point, or can we have some more better curve where it may connect some more data points and then have the connection with this particular data point? Can we try with cubic order polynomial so that the curve slightly bends more than the previous approach? Okay, then what we do? Then just improve that y is equal to beta naught plus beta 1 x plus beta 2 x square plus beta 3 x cube. Okay, beta 3 x cube. Now let us run this code and the model. Okay, and the model. Now look at this 0.7749. What was the previous one? It is 0.7729. So not much of a difference. 3.903 was the error, and here 3.97 is the error. So more or less the second order and the cubic third order are more or less explaining the same amount of variation about the y. So this is one numerical description what we can do that. I think second order polynomial is better to restrict for model prediction and predicting the age rather than complexing the model for a cubic order. But still, let us have one more understanding at how the model is. See, there is no much of a difference between the second order and third order. Okay, that's why the error residual standard error and R square are more or less the same. Okay, so with these two support, again we go with comparing method 2 and method 3. Method 2 is nothing but second order, method 3 is nothing but third order. Okay, now run this. Now see the p-value. Okay, what is the p-value here? 0.6561, meaning to that the error variability or the regression sum of squares which is observed with second order, second method and third method more or less the same. So no need to have a cubic order fitting for this particular data. We can restrict the model fitting to second order polynomial, and it will help us to reduce the complexity of interpreting that particular model. And just y cap is equal to beta naught cap plus beta 1 cap x plus beta 2 cap x square. x square. That's the requirement for this particular data. Okay, so this is a very gentle introduction to polynomial, but we can explore more and more for this. Okay, to make a very basic understanding that how to experiment different models and how to validate which model is supportive enough. Okay, whether the first method or second method and third method, like this, at every point of time, so at every point of execution, we can have a proper validating steps that we need to stop with second order, or the straight line fit is itself is enough, or we need to go for a third order polynomial. Now 3 points that we have covered in this thing. First thing is the summary statistics for the data. The next thing is the graphical presentation of the data, and the third one is model building. Okay, okay. These are the three common steps in any kind of a model building. First, look at the graph. I mean, basic summary, then graph, and then go ahead with the model building. Now, once the model building is done, use the predicted values of that particular model building and construct the straight line, and then fit that particular using the second method, and to see verify whether the first method is enough to go with the prediction of age, or second method is enough. Then we need to use a technique called ANOVA. Okay, and then when significance is, suppose at this particular level significance is not noticed, then what does it mean? The data fits per straight line. The next method what you have chosen to fit the data is more or less equal to the straight line. So the model to be chosen, which is more simpler and easy to predict and easy to interpret and easy to understand. Okay, now so here we got a significant difference between method 1 and method 2. Then we move to cubic order polynomial. Again we build the model, and again there is a smoothing lines have depicted on this particular graph. And then we go with ANOVA method 2 and method 3. Now here we observe that insignificant value, claiming that the model is final, I mean is better with the second order polynomial rather than cubic order polynomial. Because why we are choosing second order polynomial, that is y is equal to beta naught plus beta 1 x plus beta 2 x square. Why we are choosing that is the R square value of a third order, method 3 and method 2 are almost same. The residual standard error explained in the model by method 2 and method 3 are very close by. Okay, and even the graphical fit of method 2 and method 3 are more or less the same. So hence, instead of having higher complex equation, we can restrict the prediction with a method 2, which has only the x and x square version of the data prediction. So this is what we have with respect to the polynomial regression fitting. Okay, so we'll have the, now we'll switch over to the another concept, a gentle introduction to the generating random samples of this particular probability distributions, simulating random numbers from the various probability distributions. Okay, okay, let it be like this. Let me clear this. Now here there are wide varieties of statistical distributions in the catalog of the entire statistical theory and methods. Okay, now we start with basic uniform distribution, Bernoulli, binomial, geometric, exponential, okay, negative binomial. These are all comes under this kind of a, what do you say, discrete distributions with single. In the total distribution theory aspect, we have single parameter distributions, two parameter distributions, three parameter distributions. Single parameter distribution, most of the time they may depend upon location, or they may depend upon the scale parameter. Okay, when it comes to two parameter distribution, it will depend upon location, scale or shape. And when come to three parameter distribution, it may depend upon the location, scale, and shape. So what is this location, scale, shape? Location is about talking about the central tendency of the data. Scale will talk about your dispersion of the data, that is spread of the data points. And shape will talk about your skewness and kurtosis, how elongated the tail is. That's why, basing on these three important features of location, scale, and shape, we decide whether the distributions have elongated tail with the skewed patterns, or the curve is very close enough with respect to the data points. It has a pure curtic, I mean leptokurtic kind of a thing, or it is a totally flat with elongated tail. Different combinations of parameters will give us wide variety of density plots, which will talk about different categorizations of density distributions. Like we have a symmetric distribution normal, one tail distributions like T, F, chi-square, exponential, gamma, beta. Along with that, we have heavy tail distributions, okay, like Pareto, okay, like this. There, even in distribution theory, we have a huge segmentation of data, I mean distributions according to the nature of the density, okay. But more or less, I mean, most of the in general, all the distributions come under have the common features like density. It will have, we can generate random numbers from the particular, using that particular density, I mean, for that particular distribution. We can compute the cumulative probabilities of that particular distribution. We can compute the inverse cumulative values, that is quantile functions of that particular distribution. Now, okay, so the major four characteristics of any distribution is for its density, how to generate random numbers from its the distribution, how to compute the cumulative probabilities from the distribution, how to calculate the quantile values from the distribution. Okay, for example, D norm, it will give the density of that particular normal distribution given certain arguments of mean and standard deviation. R norm is to generate, R norm function is to generate random numbers for a given number of samples to be generated with mean and standard deviation. Q norm will give us the quantile functions of that particular parameters. R binorm is nothing but generating random numbers from the binomial distribution, how many samples to be generated, and the important parameters of binom is n comma p, number of trials to be conducted, and what is the probability that you are taking into. Now next comes with R poise. R poise is nothing but R Poisson. R uniform. R unif is nothing but R uniform. Like that, R exponential, R beta, R gamma. Like that, only the first letter will change and the remaining term will remain the same for every distribution. Like you see D norm, P norm, R norm, Q norm, P norm, or R binorm, D binorm, Q binorm, P binorm. Okay, so RXP, DXP, PXP, and QXP. So the letters of the first the functional letters of the function, when you change, automatically it will give the required characteristics of that particular distribution. Now, today what we see is we'll try to simulate random numbers from a particular distribution, especially for graduate student using this P norm and D norm. Given probability of x is equal to 5, okay, estimate the probability so on so function, then you can do it everything in R. Okay, very quick start, kick start for the understanding probability distributions in R. The first basic distribution where everyone chooses for generating random numbers is uniform distribution. From there, especially in heavy-tailed and skewed distributions, we generate random numbers, first generating uniform and then taking that uniform into the quantile function and then generate the random numbers. But here, we'll start with understanding the basic things of basic probability distributions like uniform, binomial, Poisson, normal, okay? Now, I'm storing the generated random numbers in UD. UD is nothing but uniform distribution. Okay, R unif of 50. When I use R unif of 50, it is an indication that 50 samples are to be generated. By default, the range of this particular argument will be minimum 0, maximum 1. Okay, minimum 0, maximum 1. So within that particular limit, because uniform distribution has the limit of 0 to 1, it's a rectangular kind of a thing. So within that, if we generate this, now my UD UD, if you see, it has generated 50 observations ranging from 0 to 1. So this number is, these numbers are the random numbers generated out of the function or unit. Now, for a thing that if you want to have a specific minimum and maximum, like minimum is 1 and maximum is 10, then automatically what will happen, it will generate the sequence series of random numbers. Let us take for small thing, I can generate 20. Okay, I can generate 20, that so that we can have a better view. And 20, then it will have like this. These are the 20 random numbers where the minimum is considered to be 1 and maximum limit is 10. Okay, uniform random numbers. Now, uh, let us use the graphical plot of GG to see that whether the shape of that uniform distribution, like rectangular, is observed or not. Let me run this for 200 sample, it is more clear. See, majority of that has a portion of this rectangular form. Okay, this is very trivial, but we'll see some more interesting features of this normal distribution. So R norm, again, R norm is nothing but when we give just particularly only the samples that are to be generated, it shows, it generates assuming that mean equal to 0 and standard deviation is equal to 1. Suppose if you want to specify certain mean and standard deviation value, then use an additional arguments, mean equal to 0 and standard deviation is equal to 1. So let us see this R norm. So it has generated random samples out of 100, assuming mean equal to 0 and standard deviation is equal to 1. Now, I'll show you one part that generating, or we can specify some mean and thing. Now see, this is the distribution of the generated samples, that it is mimicking the normal density. That is mimicking the normal density, that majority of the points are centered at the mean, close to the mean, and little or away from the center, and very few samples are at the extreme tail of the total normal density. That is why we say, when we cut this particular for one sigma limit, this is what we understand, that it explains around 67% of the data points that they are very close to the central value, and around 23, let us take 97.8 at this particular length. And when we take the extreme tail, then around 99.73% of the information, our information is covered about the data. Okay, so this is how we do. Like this, we can generate, let us take a mean of 23.212 and standard deviation of, let us take 3.323. Okay, when we do so, let us see this. See, okay, so here I'm considering more samples and bins also 100. I'm defining the bins on the x-axis should be 100. We can generate, we can hereafter we can practice or do some sort of a different exercises, reducing the bins and changing the sample numbers that are to be generated. See, if I put the number of bins as 100, because sample size is 500 and number of bins are 100, there are gaps observed. So we can reduce these gaps by reducing the bin size. Let us see. This will give better appealing than that means. So the total control is on the number, what you wish to generate, what is the mean of your data to that is to be used for generating the random numbers along with the standard deviation, and to have a proper thing that the bins should be according to the thing. It's just a common understanding that common sense of using that number of bins and the random number generation. Fine. Now we slightly move to binomial distribution, that it has three parameters when we want to generate random samples from the binom. That if you see, place the cursor, you can see that n, size and probability. N is nothing but the number of samples to be generated. Size is nothing but the number of trials, and probability is between 0 and 1. Okay. Now, if I wish to generate a Bernoulli distribution, then what should be done? The size should be equal to 1. If I keep size equal to 1 and generating, let us take 20 samples, 20 random numbers that are to be generated, it will generate a sequence of 0101 equal with a probability of 0.5. Let us see this. See 10101010. So when we, this is what we have seen, right? In when understanding the Bernoulian binomial distributions in this, the probability and distributions concept in graduate level, okay, if n is equal to 1, the binomial will reduce us to Bernoulli. Okay, so a single trial is a Bernoulli trial, and if you increase that Bernoulli trials, the binomial is of n Bernoulli trials. Now here, 10 trials I have taken, that means n Bernoulli trials are being conducted with a probability of 0.5. I'm indicating to generate it as a 50 samples. So this is a simple line of our code which will tell us that how to show that binomial distribution reduces to Bernoulli for a given n equal to 1. Suppose if I increase the binomial trials to 10 and sample size of 50 and taking 0.5 as the 50% probability of at each trial, then let me store that and run that particular graph. I'll be getting like this. Okay, I'll be getting like this. This I'm using as a bar, geom bar, fill equal to blue, width of the bar. I can change this as 1. It will have the width of the bar will get reduced. Okay, if I give it as completely 1, then you see it will create this kind of a I mean, the width of the vertical bar has been increased and giving rise to a shape of the histogram. Okay, now fine, let us keep that. Now what I did is I want to show an important property, that there is a statement that as n tends to, we might have proven a big derivation that as n tends to infinity, binomial tends to normal, right? So that we will see. Keep the same number of trials, but the sample number of numbers that are to be generated is this 50 to 100 I generated with the same probability. Now see, this was the previous one, and now it has some slight support of, okay, let us increase the width so that we can have a proper uh, equidistant tails at every point. Okay, now let us redo this graph. Okay, now see, it is coming out. Let us start from this again. Now we had some abrupt kind of, I mean, there is no proper shape and it has some right skewed kind of a thing. But when we increase the sample size, okay, when we increase the sample size, it is attaining at most similar, right? So some points still it is not that equidistant. Now let me increase the sample size to 500. As n goes on increasing and increasing, let us see how the binomial distribution possesses the symmetric nature of the normal pattern. Okay, this is when compared to the previous sample size. Now the sample is increased to 5,000. Now it is very different. I mean, when compared to the previous samples of 500, and now this 5,000 sample is mimicking the nature of the normal. Let us do one more experimentation, increasing 10,000 samples. Okay, now see, this is almost exactly normal. This is exactly normal distribution. So in 4 lines of our code, in 4 to 5 lines of our code, we were able to show the practical part of the theorem, what we have derived, that as n tends to infinity, binomial distribution tends to normal distribution. So this is small exercises where a graduate students can do and learn the practical part behind every mathematical framework. Okay, right? Now, another exercise what we can do is, suppose so far we have done that with probability 0.25. Okay, probability 0.25. Now when we do the probability 5, and now if I make the probability to 1/4, how my data look like. Okay, how my histogram will look like this. Now see, when the probability is around 0.25, it is slightly skewed on the right. It is slightly skewed on the right, meaning to that the majority of the observations are at the are above the 25th percentage of that particular region. Okay, now let us do that in a reverse way. That 0.75, the curve should come to the left hand side, showing some slight skewness to the left hand side of the area rather than the right side of the area. Now see, okay, so this is what pattern that basing on, this is all a game around the probability value. These are all different exercises where the graduate student has to do so that they will understand actually what kind of derivations we are doing, which are connected to the relation behavior of the distributions like binomial to normal, Poisson to binomial, and there are different many relations between each and every distribution that can be sorted with a simple R code. That this is what we mean the statement refers to. Okay, fine. Now we'll go with the Poisson distribution. Okay, here what is that? R poise, n equal to 100, lambda, some rate of some lambda I have taken, 13.5. So ggplot, these are all the arguments which are used for depicting the graph. Okay, let me generate 100 observations with the 13.5, and let us see the graph now. This is the plot of this particular Poisson plot, and then let me increase the sample size to 1000. How my the pattern of Poisson distribution look like? It attains normal. It attains normal. Okay. I mean, in n is number of is 0, 1, 2, 3, and so on. Right. Now let me increase further more. Okay. It will come very closer. The density of point C, it comes very closer approaching the pattern of normal density. Some more observation, 10,000 observations, but here I have changed my mean. I have changed the lambda, that is, which is equal to location, the mean and variance of this Poisson distribution. I have reduced that 13.5 to some 4.5 value, giving out the meaning that what pattern it will tell. It is slightly skewed on the right. So actually, this can be shown very easily, that how, basing on the variation of the parameters, how the sorry, the density of the distributions do vary. The density of the distribution do vary. So that's what, with just random number generation, we are able to witness the relation between several distributions, binomial to normal, Poisson to normal, and then we can do some more exercises. It's just introductory part. We can do some more exercises, and especially it is the practice for the graduate student that you can do lot more, working with a single line of R code to see how the one distribution approach to other distribution by changing the parameter and increasing the sample size. Okay, now this is the small one, and similarly we can generate this exponential also. Okay, we can generate exponential also. How it will look like is this. Exponential is a skewed distribution, right? Skewed distribution, right? We can generate more number of samples. Okay, and more number of samples here, and then it will show nice pattern of the extended tail version of the exponential distribution, and mean is located here. So that's why this is the central location parameter. If I have a density plot for this, it will come like this and it will extend like this. If I increase 5 more, furthermore, I will get a very smooth and kind of a histogram that this is what we have. Now what happens if I make a rate equal to 1? If I make rate equal to 1, what will happen? Okay, so there is no much change because rate is different. Now let me increase the rate to, let us take 14.2. Okay, so it is, what we have done is different now. 1 minute. So the as sample size increases in random number generation, we can nearly show the proper approach of this tail and extended tail of this exponential distribution. So with this general introduction to this random number generation of simulating random numbers from different distributions and nonlinear regression, I stop my presentation. I will open the floor for 10 minutes for questions. Okay. Okay. Already there are questions. Yes. Yeah. True, sir. Shiv Shankar sir raised a question that nonlinear regression models are often used in chemical laboratories. Yes, it is true. In most of the life sciences and the medical sciences, we observe the reaction rates which are non-linear, where we have to use such kind of a experimentation of model building. How can we calculate correlation matrix between numeric data and categorical data? We cannot. See, the major thing is correlation can be computed in 3 to 4 different segments. Number one, when you have single population and you have a 4 to 5 variables, or let us take 3 variables at hand, then you can compute using a Pearson's correlation. If the data is rating, then you can use Spearman's rank correlation. If you have the rating data, that is before and after, that is analog to the paired sample t-test, before and after rating, then you can use McNemar test. Now coming to the correlation, you have two populations, but you have 2 to 3 variables, the same set of variables on both in two population. Then you use a extensive technique called advanced technique called correlation, canonical correlation. Okay. Now, and you can compare the two population correlations using Z statistic. But to the best of my knowledge, we cannot compute the correlation between the numerical data and the categorical data. Only for numerical data alone you can do the correlation. Thinking, what is the, how can we make the difference between SRS and, so simple random sampling with replacement, simple random sampling without replacement. Okay. Now, it happens that you have 100 samples to inspect. Okay. In especially quality industry, simple random sampling without replacement happens. Means most of the time that simple random sampling without replacement is that you have 100 samples, 100 goods to be inspected, and you take 10 samples to check whether the total lot is good or not, and then you inspect the 10 goods. Okay, and you won't keep back. Sorry, let me correct. Simple random sampling is nothing but once your goods are inspected, those samples will be kept aside, and the remaining samples will be again taken for picking the samples from the remaining lot. Okay, simple random sampling with replacement is that picking the samples from the lot and inspecting, and all the good ones will be kept again into the lot. So again, some more samples will be generated. Coming to the most of the time in probability random, in bootstrapping or generating random numbers or selecting some samples from the available data, we go with simple random sampling with replacement. Especially in bootstrapping, we go with simple random sampling with replacement. RSS is the regression sum of squares or the residual sum of squares. It talks about, I think, residual sum of squares. It is about residual sum of squares. What is the difference between R square and adjusted? Yesterday I have explained this R square and adjusted R square. That in R square, it is the regression sum of squares by the total sum of squares, and in adjust star square, the denominator where you have the instead of correct total sum of squares, it is we have corrected total sum of squares. Okay. I of length is nothing but a defining, indicating that length should be of square, x square. Lambda is the parameter of the Poisson distribution. How to handle missing values are there in data? Yes, sir, there are many packages available in R. Okay. I vaguely remember mice package is available, and then multiple imputation techniques, that is what we call multiple imputation techniques, you can handle. There are packages available. How to handle means it is a big discussion. Sorry. Thank you. Yes, yes, exactly. Given when you have a data in your hand, I mean, when you have your experimental data, the first step is to have a graphical view of the data. That data, that graphical plot will make us understand that the pattern existing in that particular, I mean, the pattern existing in the data points and how they are related to each other, and how the trajectory of the data points are there across the xy coordinate, and so on and so forth. Okay. So the best practice is to may have the scatter plot and then go for modeling. Can we do the same queries for two samples with different sample sizes? Can plot them. Two samples with different sample sizes. You mean to talk about two sample t-test. We can use box plot to plot the two groups of samples. Not necessary. Just I have used a ggplot too. For the generating random numbers, just no package is necessary. You can use R uniform, R normal, or anything. But the ggplot I have use it to show you the pattern of the distribution, how it is exhibiting. That question. How do we check significant difference in correlation of two variables between two samples? Okay, let us take x1, x2 is, uh, sorry, x1 in one population, same variable is observed in x2. Okay, then to see the correlation between two population, you have a Z statistic application. Okay, Z statistic application. Convert numerical data sets to rank and then undertakes pair-band rank correlation. Okay, thank you, madam. Thank you. But converting numerical data into categorical data sets and then rank them, that is also correct way. But they should not overlap. I mean, what we say, they replace the numerical data with the categorical. They should create a new variable of the categorical. Okay, so that the original data will remain safe. Okay. Yes, ordered data is nothing but rating data, that is Spearman correlation you can do. Is there any book? There are wide varieties of books. Um, each for every domain of statistic, there are books available. Like when you take time series and data analysis, and there is a book by Stopper and Shambe. Ecological statistics is there. Biostatistical analysis is there. Epidemiology and biostatistics is there. Okay, where all these techniques are available. Okay, it depends upon your domain of interest, in which discipline you want to learn. Okay, like you have management text statistics for management out there. Okay, thank you, madam Ranjita, madam, thank you. Sir, for COVID prediction of future values of COVID-19 data, which type of statistical technique we use? So the normal statistical models are not that useful. There are some separate, what we call is it makes use of one particular variable concept called reparation rate, if I'm correct. Okay, using that, there are some different varieties of models, not the models what we have discussed. Okay, uh, I take is nothing but indicate that this I of is used to define the variable as x square. That's what, madam. In this now in the nonlinear plot, okay, we had the majority of data points connected to the fitted line, right? There is one point in the upper top corner that is which is away from the common density of the curvilinear plot. So that is what we call extreme point. But along with the trajectory, there was one more data point, but it is not connected. That is what we call outlier. Outlier is observed within the same density of points. Okay, extreme value is above that particular contour. Reparation rate, reparation rate, I think so. I was reading that the university of some other university, University of Michigan, there was a study that reparation rate range increased from zero point 0.3 to 1.3. That was a huge jump in reparation rate of transmitting the COVID cases. Canonical correlation, it is observed. See, let us take three variables like hypertension levels. Okay, x1, x2, x3 is observed in two populations. Let us take group 1 and group 2 are two populations. In both the populations, same characteristics are measured. Now, if you want to have the correlation between two groups of population, then we have to use canonical correlation. Okay, and the canonical correlation is totally works out with eigenvalues and eigenvectors. Principal component analysis, canonical correlation, these are all the beautiful techniques, very important techniques where you focus on eigenvalues and eigenvectors. My mail ID, okay, we are statsguru@gmail.com. Very basic question. Can you tell the real life example for variation in data? Okay, simple. Uh, I'll take cricket data. Let us take one batsman's 10 records. Okay. In first innings, first match, he has scored 25. Second match, he has scored 10. Third match, he has scored 100. Fourth match, he has scored 70, 50, 20, something like this. Okay. Now, if you observe the standard deviation, can you observe, if you observe, compute the standard deviation, or how you do the standard deviation xi minus mu. Okay, mu is nothing but the central value of that particular 10 data points. So the difference of xi, each data point to the mean, is nothing but the variation exhibited from each data point from the center to the actual data point. Okay, that is simple to say, it is a spread from the center, difference from the center. Can I explain sensitivity analysis with PRCC method with dependent variables versus? Uh, so, you wish to explain, or what is the PRCC method? Can I know the expansion? I am not able to recollect what is the expansion of PRCC. Anil Chatterjee ji. Anil Chatterjee. What is it PRCC stands for? Sorry, I am not able to recollect it. Okay, I think it's not there. Anyway, with this, we'll close the session this afternoon, 3 o'clock. We'll meet again. Okay, 3 o'clock, sharp 3 o'clock, we'll meet again to discuss some more points, aspects. Okay, thank you.